So the RMG website is an interactive website that sort of is intended to go along with using RMG. So the website runs RMG in the background, and while you can't run RMG jobs on the website, you can do a lot of other stuff, such as using some of the scripts, as well as searching the database, so on and so forth. So in this session, I'll just walk through some of the features of the website. And so the website is at rmg.mit.edu. And you're welcome to follow along. One sort of caveat is that this website is hosted on our own server, which has somewhat limited computational ability. So if everyone tries to do something at the same time, it might not go so well. So just be aware of that. But you're welcome to follow along. So I guess first, I'll just go through the sections on the left. So first is the documentation, which is technically a different website. So it's hosted on GitHub, and it provides all of the RMG documentation as well as the Arcane documentation. So I don't know if we mentioned this yesterday, but Arcane is sort of a different software package that is included within RMG, and we use it to do like thermochemistry calculations or transition state calculations, transition state theory calculations using quantum chemistry. So that's part of our overall workflow, where we'll do some quantum chemistry calculations and then use Arcane to get thermo or kinetics, which will then. Okay. But in the user's guide, yesterday you probably looked at the installation section of how to install. We also have a lot of information on how to create the input files, all the various sections, which I think Matt went over yesterday as well. And then some of the outputs, guidelines, and then a lot of the standalone modules for other functionality that RMG provides to help you with generating these models. And then discussion about the databases, these for different versions. So if there's something that you're trying to do in RMG, I would probably stop right here first and see if there's anything that covers that. Similarly for the Arcane user's guide, if anyone does end up doing quantum calculations or wants to calculate tracer thermo, this is very useful. The theory guide goes a bit more in depth instead of how the code works. It's the actual underlying algorithms behind RMG. So this, especially the RMG theory guide, this could be helpful. And then the API reference is mainly for developers. So this is a list of basically all the modules within RMG. And then you can go in and look at all the methods of those different classes. So kind of find a function that does something. And scripting on your own can be very useful. Okay, so then all of this is on the sort of documentation side listed on GitHub. And then everything else is part of the actual RMG website. So first, we have some additional resources. So links to some of the publications, or like the core publications that where we publish how RMG works, RMG itself works. There are other publications where we use RMG, which maybe we should ask here. But bulk of this page is the RMG study group presentations. So we haven't done these in a while, but yes, the last one was a little over a year ago. But these used to be a way for developers to sort of share information about various aspects of RMG. It was mainly for other developers, but some of them might be useful to you now, such as information on how to build models, about the agency list, which, so at one point we revamped the agency list to what they are now, adding a lot of new features, and then liquid reactor, currency analysis, Some of the very early ones, like from 2013, might not be as applicable. Models changes, but they're still good reference if you're interested in any of these topics. Then the RMG database. So this is probably one of the nicest things about the website is that you can browse through the database in sort of a graphical format rather than through all the text files. So some of the files are a bit large, so they can take a bit to load, but this is very useful. For example, in the Kinetics database, you can look at all the libraries. So this is a list of all the Kinetics libraries that are currently in RMG. So we have the library name, how many entries it has, and then some of them will have a description. So then you can click into a library. And then it has a longer description here, and all of the reactions that are in the library. So here we draw out all the reactions, so you can tell what they are, and then you can click a reaction to get the kinetic. It might take a bit. And in kinetic families, similar. So this is the list of all the kinetic families that are currently in RMG. There are 6 of them. So you have the name of the family, and then this is essentially content of the family, which I'll tell you a little bit more about in a minute, and then a schematic showing the reaction recipe, or exactly what this family defines. So for example, you can see super common one. This proportionation, for example, is defined as a radical and another radical with hydrogen, and then turning into two stable species, one with the hydrogen and one with the sulfide. So this is a good way to look through the available families. If you're interested in a particular reaction, you're wondering which family it might fall under, for example. Another thing I'll get to later is the kinetic character, which is also useful. And then sort of to explain this intersection, the groups is basically the templates that we have defined for this family. So more groups is generally a better elaborated family, so it has more details. Rules is the number of data points. So these are rate rules. So the more, again, the more data is in the family. List and training are depositories. At some point in the past, we scraped all the kinetics data we could permit in this depository, and training is the depository that we could add, that we train these families. So yes, we'll be talking about training a bit later, but just think of it as data that we use estimating rates. So this is a specific reaction that I just picked from this family, and you can see again we have the picture, has the rate coefficient. This link will let you search for other kinetics. It goes back to kinetic search, and I'll get to in a moment. So that's sort of the kinetics part. And then we also have a Soliton database. So RMG does have some liquid-based capabilities, and the Soliton database will let you search for solvation corrections for a relatively limited set of solvents. But I'll get to that with solvation again. The StatMax database is for pressure dependence measurements. So RMG has so during normal RMG runs where you use pressure dependence, RMG will try to estimate the frequencies associated with all your species in order to get the pressure and kinetics. And then the StatMax database has information to estimate those. And then thermal database is the other major component. So, and then here the main parts are the libraries and the groups. So the thermal libraries we discussed a bit yesterday. So this is a list of all the libraries. And again, you can click into one. It'll show you all the species that are in it. Also, format of the data. The group additivity just means standard thermal data format, which is just H298, S298, and CP, variety of temperatures. Whereas NASA, of course, is NASA polynomial. So click in. These are the database of group additivity values. So we have the base values, which you can see has a ton of entries, and then other corrections, so long distance corrections, and ring strain corrections, radical corrections, and so on. And again, you can click into these. You can see the template that it codes for. So note that these pictures look very different. So it's because these are group definitions instead of molecules. So I don't think we really covered that, but molecule, of course, is an actual species, chemical species that you can represent. A group in RMG is the substructure. So, for example, this is just these 3 atoms that are of certain types, and then the actual molecule that matches this can be much larger. So these are, I clicked on ring corrections. So these are all different sizes of rings with different types of atoms, and for each of them we have a contribution to the group additivity. And then finally, there's a transport database, which has comparatively less data than kinetics or thermo, but we do generate transport parameters for all of our species for people who do want to do like CFD or engine simulations. And you can download the database with just download the GitHub. Are there any questions?
Thermodynamics is the temperature is like 2000 K, and beyond is you don't have the data on that temperature or specific like pressure in that condition.
Mm-hmm. Can you repeat the question?
Right. So you're asking, since we don't have data above 2000, what do we do about the thermo? Well, so for example, in some of the libraries I showed, with this type of data, here's saying like here we don't have CT above 2000. So I think we will extrapolate. So the RMG can calculate a CP0 and a CP infinity. I don't remember the exact equations, but they're theoretical derivations, right?
And not only CP, like the other like pressure is too high, more other than CP pressure. And well, I mean, some value, something you don't know what it is, just use the equation to extrapolate it and do the calculation, right?
Sorry, I'm not sure if I understand what your question is.
Okay. Maybe stupid. Just it seems like you don't have exact value. Just use the equation like some formula to get the
right. Right. So so you're saying we don't have like a tabulated value of the thermal properties at each temperature, right?
Yeah.
Yeah. So I guess from enthalpy and entropy at 298 and the CPs, you can calculate it. So these equations are theoretical, so they're not like fitted equations, right? So you can I don't remember what the name of the equations are, but from there's an equation for how to like take the H298 and you integrate over CPs up to whatever temperature, and that gives you, for example, enthalpy at 2000. So that's why the sort of default thermodynamics parameters in RMG are these set. So the H and S at 298 and then the CP. NASA polynomials are a bit different in that they are essentially fitted. So you can see under NASA. So they are these and then their functions of temperature. So then these are typically fitted to, so if you're, for example, doing quantum calculation, you'll evaluate Cartesian functions and get your thermal at quantum temperatures, and then you'll fit NASA polynomial to all those temperatures. And then if you just provide RMG with the NASA polynomial, will evaluate it at whatever temperature. I hope that answered your question. Right, so this is the database section. And then molecule search, I think Mark showed this a little bit yesterday. This is very useful if you're wanting to draw smiles, for example, or for a molecule you want to search thermochemistry or transport. And we recently added a function to generate residence structures. So this might not be useful to mostly at this point, but it's definitely useful if you want to investigate more in detail how RMG is generating some of its reactions. So actually, I'll show this first. So you can actually draw a molecule to input. For example, if you don't know the smiles, or if the name isn't turning up with the species that you want. So, right, basically you can put whatever you want. You can add radicals, lone pairs. One thing to note is that right now this is a bit limited, so you need to explicitly add lone pairs. So I think that oxygen has 2 lone pairs. Yeah. So this comes out correct. But if I were to just draw it without anything, then it's actually invalid because it thinks the oxygen is missing electrons. But, right, so you can draw things, and then you can search the thermochemistry. I can search thermochemistry, which will give you all of the results from all the thermo libraries as well as group additive. So this is a good way to compare thermo between different sources, or if you want to see which library maybe you want to include in order to get accurate thermo for some species. So here we have one result that's from this library, JetSurf, CHO, BioOil, all of these different libraries, and then very last result is the competitivity result. And then we have these plots which compares all of them, and you can see in this case all of them match very well, including competitivity. Although, for example, in heat capacity, the group competitivity values end at 15 or 32,000. Again, that's because it's in thermal data format, whereas these others go very far because they're not the polynomial. Right, so that's thermal search. You can search for transport properties, which will give you like the shape index, epsilon sigma, which you need for if you're doing any sort of CFD. In this case, generated resonance structures won't be too exciting. So we have this one representative structure. We recently changed RMG so that we prioritize these aromatic structures over the calculated structure, since that gives RMG a better idea that or we're able to handle it more accurately by knowing that it's aromatic. This is something that might be a bit more interesting. So here we can look at these resonance structures, and basically we have a ton of these unrepresentative ones, which aren't aromatic, and then these other ones. And so the importance of resonance structures in RMG is to be able to properly capture all of the different reactivity, potential reactivity of a molecule. So in this case, we had this radical species, and because the radical is conjugated with the aromatic system, it can delocalize around, and then we try to capture that by considering all these structures where the radical is in different locations. And then that way, when we generate reactions, we can show or properly identify reactions where each of the sites with potential radical character are reacting. So sometimes, if you're not getting a reaction that you might be expecting, it could be because we are generating a resonance structure that leads to that reaction. Right. But this is going a bit too much in depth into details of RMG. If you're just using it, it's probably not that important. Okay, so then the next part is kinetic search, and so here you can basically search for kinetics for any reaction. You can specify one reactant, two reactants, and without any products. If you do specify products, you need to specify all the products. So if you have, for example, bimolecular reaction of two reactants and two products, you can't specify two reactants in one of the products, since RMG is not going to be able to figure out the fourth product or the second product. So we can do something simple like do an H abstraction, or maybe we're looking for H abstraction between octane and OH. And then we see we have 4 different reactions. Makes sense since there are 4 different sites you could abstract that from. And you can look at the results, and it will give you, again, all of the library results. So I guess only in JetSurf. And then these depository results. So from this, we have a couple of rates, and then we have rate rules and group editing. So right now in RMG, the primary recommended estimation method is rate rules. Group additivity is somewhat just there. It was developed at one point, but then I think one of the developers concluded that it didn't do as well as rate rules, but we just kept it sort of kept it there instead of removing it. But then again, we plot the kinetics. You can see that group additivity is very different. It sort of supports that. So hide that for now. But then yeah, so we have all the different rates from libraries and the rate rules, and the dotted line is an average of all of them.
What's the difference there between 6 and 8?
Oh, right. So between 6 and 8, so this 8 is marked by a star, which says it's kinetic fitted from the reverse direction. So what this means is, so for H abstraction, it's one of the a set of families that are their own reverse. And that means that the forward reaction and the reverse reaction have the same template, or the same set of steps to occur that necessary for it to occur. So basically, regardless of whether you're going forward or reverse in the H abstraction, one radical is taking H from the other molecule. So in this case, 6 means that we estimated this in the forward direction. So when we searched for the rate rule, we were looking for OH radical abstracting from octane. And then so we found the rate for that. And 8, we estimated from the reverse direction, which means we were actually looking for this 1 octanol radical abstracting in hydrogen from water. And then we take that rate and then use the thermo to fit the reverse rate and to get it in the direction that we asked. So basically, 2 different ways to estimate the rate from the same family. And in general, estimating in the direction that we want it should be more accurate. And we can see if that is true. Yeah, so this line that lies below all the others is the one where we fitted it in the reverse direction. And then the red line. So this red line is getting it from the forward direction.
Okay, so the experimental ones are 1 and 2, is that right?
So these are from the jet surf mechanism. I'm not sure if they actually use an experimental value. Then this result might be experimental.
I was just wondering for those if they fully take into account the fact that micro rate constant or radical reaction.
Right.
So that's why I was wondering if there's different, that the reasons the difference between Gordon and those.
That's possible. I'm not sure exactly what these sources were, but we could potentially look them up to see how they got those rates. Right, and then we can also click into here, and it just gives you a specific page with the descriptions, which can be useful. Or of limited use. So for RMG estimates, we'll tell you which rate rule it came from. So I think Matt went over this a little bit, but like the Euclidean distance is how far the final rate rule that was used is. So how far that one is from templates that our reactants match. So the farther it is, that means we didn't have data at the thing that matched the best, so we had to go a bit farther to find something that's reasonably close. And then the top of the grading. And then we need something that gives more reaction. Then there's Soliton search, which you can use to get population corrections for various species. So you can give it solute, and then we have a list of different solvents. And you can get these parameters, which, to be honest, I'm not very familiar with, but basically, RMG uses these to do the liquid phase simulation and get solvation corrections for thermo and kinetics, I think, as well. Maybe just thermo. So then this second to last section is pressure-dependent networks, which is sort of graphical interface to most of the functions of Arcane. Actually, that's probably not true anymore, since we added a lot of functionality to Arcane recently. So this is somewhat unique in that it's the only section on the website that you need to have an account for. So you have to create an account. Right, and then after you create an account, then you can upload, you can create new pressure-dependent networks. I uploaded, this is just one of the RMG examples, which again might take a bit to load. Oh, here we go. So you can upload a standard Arcane input file, and then you can run, or you can plot the potential energy surface. You can also run it to get the pressure-dependent kinetics. So basically, you can do everything here also from the command line using Arcane directly. And you also get the same plots, but this can be a useful way if you'd like to do it graphically. If you click in the species, for example, you can see all the statistical mechanics parameters. So, like vibrational frequencies, rotation, and then this species has hindered rotors. You can see the hindered rotor potential. And you can download the alpha file after you run it, which will be the same as the Arcane alpha file you get running locally. Again, because the website runs RMG and Arcane in the background. Right. So the last section is these other RMG tools. Some of these are probably not useful anymore, but there are a couple of very nice tools. So most of these are also available as scripts from RMG Pi or RMG Database. I think mostly RMG Pi, and we'll be going over the scripts in a later session this week. So this first tool lets you convert a ChemCon file to an HTML file, which I think you've already seen some of the HTML files that RMG can generate. If you choose not to have RMG generated during your job, you can do the conversion after the fact here. We can also compare models, but you just provide two different ChemCon files, and then we can do a comparison. Show an example. So you need the ChemCon file and RMG dictionary, or output whenever you run an RMG job. And then we'll compare them and give you the HTML file. And so here we see basically there's one model on the left, one model on the right, And first, it will compare all the thermo. You can see these all have the same thermo. So these have different thermo. And we can gives you the comments, so you can see in the first model. So this is just a minimal example. The first model used group additivity, and then the second model, in which I turned on the machine learning thermal estimator, we can see we got a machine learning estimate for this thermal, and they're a little bit different. And then you can also see the second model ended up with a lot more species, and then we also have a reaction comparison. So similarly, if they have this identical kinetics, or in this case they had different kinetics, and you can look through the comments, and sometimes you can tell why they're different. In this case, I'm not sure. Yeah. I won't spend too much time on that. But and then at the very end, you get the list of reactions that were only in one of the models. Right. So if you're running a lot of iterations of a model, this is a good way to see what changed between iterations. And again, there's also we also have a script for this if you want to run it locally. So we have very, very large models, like hundreds of species. Then I would advise running it locally because the website has been known to crash or just not load if you give it too big of a model. Right. So this third one I won't go into. So it's mainly for compatibility with RMG Java.
Matt, we have a question that maybe you can reply to everyone.
Yep.
Does this mechanism comparison works for mechanism not generated by RMG?
That's a very good question. It does. I don't have too much experience doing that. But you can see here, you can select that it's not an RMG generated ChemChem file. I think you still have to provide an RMG dictionary. Because the key, so what this option will do is basically we won't try to read any ChemChem comments, and we'll just load in the kinetics and thermal parameters and compare them. The reason you still need an RMG dictionary is that in order to compare, RMG has to know what a species is. Otherwise, we won't be able to see if the species or reactions are the same. But if you are able to prepare an RMG dictionary file, then for any ChemChem file, we should be able to compare that. So then we can also merge together two models. So the input here is basically the same as for comparing models. You get two models using the ChemChem file and RMG dictionary, and then RMG will go through all the species and identify any that are the same, and then it won't duplicate those, and same for reactions. And this can be useful if you're trying to generate a very large model sort of in different parts. So you might generate a sub-mechanism for two species and then generate another sub-mechanism for one of the species plus another, and then merge them together to get a overall mechanism. And again, there's a offline script for this. I think in that script, you can actually merge together multiple models, so you can provide like 3 or 4, and they'll all merge them all together. And also ignoring all the overlapping species and reactions. Oh, and one thing to be aware of in choosing, so if you do have an overlap, and for example, 2 species and they have different thermo, or 2 reactions and they have different kinetics, they'll prioritize the first one. So if you're merging 2 models and you have higher confidence in one of them, or higher confidence in the parameters that one of them uses, you should put that first, and then it will prioritize those signals. Generate flux diagram will give you a reaction flux diagram. I'll run this. I don't know. It might take a while. But it will give you a video showing the reaction as it progresses throughout your time. So you need the So you still need the mechanism by writing ChemChem file and RMG dictionary, but in this case you also need to add in an RMG input file. So this is typically the input file that you use to generate the model. And the reason we need that is for your reactor condition. So I might just, okay, so I timed out on the kinetic phase. So while the flux diagram is running, populate reactions. This is essentially a single iteration of an RMG run. So it's similar somewhat to kinetic search, but it gives you all the reactions between your input species. So a typical way we'll use this is if we want to find out if or all the possible reactions and see if we're getting the particular reaction that we're looking for. You can provide, so it looks like a standard RMG input file. You provide all the species you want to find reactions between, and then it will just react all of them and then end, instead of doing the normal process of reacting all of them, simulating, and then iterating. So it's sort of half of the RMG iteration. Again, this is available as a offline script. It's finished. So again, this is the minimal example, and it generates this video of your reactor condition. If you have multiple reactors, it will actually give you multiple videos at each of the conditions. And you can see we have ethane pyrolysis going to all these products, and then the arrow showing how much flux is going through that pathway. Yeah. So as with basically all of these tools, if you have a very large mechanism, we recommend running it locally. So this script is also available in RMG. Kinetics. Basically allows you to talk kinetics using a ChemChem file. The dictionary. So dictionary will draw the species and also let you search for. It will provide links to the RMG database. So I don't have an info prepared for this, but basically you probably only want to provide like a single reaction or maybe two. I could upload the entire minimal ChemChem file and it'll work, but we'll just get a ton of lines from the file. Again, RMG Java compatibility, which probably don't have to worry about. Massive polynomial evaluation. So this is actually really helpful if you have an arbitrary massive polynomial that you just want to plot. They aren't very user-friendly to just read in plain text. Actually, I'll just copy one from. So if you have a massive polynomial, another mechanism or something, you just paste it here. And we'll convert it to thermal data format, and also give you all the plots, like we do for all the thermal entries. Yeah, so this one's very straightforward. And then drawing a functional group. So I mentioned earlier the difference in RMG between a group and a molecule. So this lets you draw groups as compared to molecule search or draw. So molecules. See if I can find the group. Basically, it will generate. It generates these drawings. So this is mostly useful if you're planning to add data to RMG database or develop new groups. But I don't actually know. Okay, so you take in the vacancy list and you paste it here. It will try it. So very simple, but for us, when we're adding a lot of data, this is very useful to try and figure out what these vacancy lists actually represent. Okay, so seems like this doesn't want to load. Maybe I should try smaller things. But basically, that's it for the website. Are there any questions? Anyone has?
There's one question from the website regarding the flux diagram. Does the website use a particular tolerance to generate the diagram? Are all species there?
Right. So there are settings that you can provide. Yeah, so in this advanced options block here, you can pick the maximum nodes, which are the number of species that will be included in the flux diagram. And I think this will cut off based on concentration. And maximum edges, so the number of reactions that you want to draw. I think this, I'm not exactly sure what this affects, the time set factor. But then you have the concentration tolerance, which will limit what species you show based on concentration, and also the rate tolerance, which will limit which reactions you show based on the rate.
Thanks.
How do you do the potential energies of this diagram?
Right. So under pressure-dependent networks, if you upload a file, then on the left here, you can draw the surface as PNG, PDF, or SVG. I can also try uploading a new one. And then updated my RMG. That's not good.
And those input files can be built from using RMG. So we installed yesterday.
Well, so you have to put the input file together manually. We don't have an input file generator, but you can see examples. Like, alright, I will update my RMG.
Or show from GitHub.
Oh yeah, I'll show you from here. So in our RMG example, we have this arcane folder, which contains a lot of examples for input files for arcane. So if you're looking at networks, this is an example. So this is technically not part of the session, but you define species and you need to provide all of their StatMac info, and then you also need to define transition states, reactions, etc.
I might not be understanding very well, but arcane file is totally different from Java.
Yes, Arcane is completely different from Chemcam. So Arcane profiles, well, to specific Arcane, they're defining sort of using quantum data to evaluate thermokinetics. So like we define here all the vibrational frequencies, energies, stuff like that. So it's sort of it's a different step or different process than reaction generation.
Oh, so that's, so it's kind of software, like Gaussian?
So it complements Gaussian. So it's sort of the intermediate step between running Gaussian and then having a rate for a mechanism.
Yeah.
So.
And I may just also add about Arcane, there is lots of documentation on the RMG website, as we showed in the beginning of this session, Max showed. So everything in the input file is also explained there.
Yes. So Arcane isn't a necessary part of running RMG. I probably got into a bit more than I was planning to, but if you're interested in running Arcane or running quantum calculations, you can come talk to us. If there are any more questions, I think we'll take a short break.